Today's lesson is about composition of functions. But before we do that, let's take a step backward and look at combination of functions. So just like we had operations for two real numbers like addition, subtraction, multiplication, division, today we're going to do the same arithmetic operations, but we're going to do them on functions. So suppose I have a function f of x is equal to 2x minus 3 and g of x is equal to x squared minus 1. I can do all of the mathematical operations. So like I can do addition, and that's going to give me 2x minus 3 plus x squared minus 1. Then I'm just going to simplify it, and that's going to be the addition of two functions. Now sometimes it can also be represented as h of x. So what it's saying is that when you combine two functions f of x and g of x, you get the third function h of x. So let's do the same thing. If I had f of x minus g of x, I'm just going to take f of x and then subtract g of x. Note that I have put the parenthesis. That's very important because otherwise it'll lead to an algebraic error. So again, I'm going to simplify it. I'm going to distribute. And then I'm going to get, and that is going to be my h of x. So all of the operations that I do on real numbers, I can do with functions. So if I were to generalize this, what I would say is if I had f of x plus g of x, it is like saying f plus g of x. Same thing for subtraction. F minus g of x, and f of x times g of x is f g of x, and f of x divided by g of x is, and of course g of x should not be 0 because you cannot have division by 0. So if you were asked to find, given two functions, let's do an example here. Example, I have a function f of x is equal to 2x plus 1 and g of x is equal to x squared plus 2x minus 1. And I am asked what is f plus g of x. I'm going to go back to my definition, which is right here in the box. And I know that it is f of x plus g of x. So now I'm going to substitute. And my answer is going to be x squared plus 4x. So pretty much whatever you can do with real numbers, you can do with functions, but you have to be careful about the domain that all these functions are defined in. So it's important to make sure that we kind of adhere to that constraint. Okay, here everything is on real numbers, so it doesn't matter. Okay, so now to the real point of this lesson, which is composition of functions. Okay, so composition of functions is needed because let's take a like a simple example to understand this, right? So let's say that there is a farmer, and every year he plants seeds that turn into corn. So he wants to write a function for that. So then he says C of A is this. So that means if he plants corn on A acres of land, C of A gives him how much he produces of the corn. Okay, let's say in kilograms. Okay, yes, he's interested to know how much corn he produces, but eventually what he wants to know is how much money will he make from selling that corn. Okay, that's really what he is interested in. So then he finds out that this is the equation. So if where m is money, which is a function of the corn that he will sell, that's why the C. Same thing here, it was how much corn you're producing is a function of the acres of land you plant the corn on. So if he produces C kilograms of corn and he puts that value into the equation, m of C represents how much money he makes. All right, so let's say that he produced 13,500 kilograms of corn. So then he puts that value in the equation, right? And when you evaluate it, he knows that he makes this much money. Now, you notice that to do this, he used two different functions. So he used this function and then he used this function. Now, if somehow he had a way to just use one function, right? So that he did not have to do the two things. So like if you were to think about it visually, he had 2 acres of land, then he planted the corn and he got 13,500 kilograms, and then from that he got $12,100. So instead of going through this two-step process, what if he could just go from here to here? Right? That's the question. So let's see, can we create a new function? So the new function could look like this, right? So he takes the old function which kind of told him how much corn he produced and put it into the money function, then he's going to get it. So that's a way that he could just do it in one shot, right? So if remember how we defined m of C? It was 0.9 C minus 50. But now, instead of just C, that is the kilograms of C, I'm having a function that calculates the kilograms. So wherever the small c was, I'm just going to replace it by the function, which gives me the answer. It's going to produce the same thing, but this is more of like a one-shot way of doing it. So in some sense, this is why composition of functions we use. This is like a more practical example. And now we will look at like how to represent it using just f and g and just generalization. Okay, so if you have an composition of functions is denoted by this little circle, and the way it is read is f of g of x. That is how you read this, f of g of x, and this is the symbol. Okay, this is the symbol. Now, how is this defined? F of g of x is defined as f, but instead of just having a variable, we're going to have a function. So we are very used to f of 2 or f of 5. We had only numbers here, but now you're going to have a function as the input. So this is a function as the input. Okay, that's really all there is to composition of functions. And the domain is very important here, right? So what is the domain of f of g? It is the set of all x in the domain of g such that g of x is in the domain of f. So what does that mean? Is that you have to consider both of the domains, right, of f of x and g of x. So let's look at an example now. Okay, so let's look at an example. So let us say that f of x is x plus 2 and g of x is 4 minus x square. Now I need to find out f of g of x. Let's do it one by one. So let's do f of g of x first. So when we want to do f of g of x, let's look at the definition of f of g of x. What is that? Your first thing, f, and what is taking as the input is the function g of x. So that means I first write out f of x. F of x equals x plus 2. Now, wherever there is x, I need to put the function g of x. That means if there is x, I literally replace it with g of x. So if when there's x, it's 4 minus x square plus 2. So that becomes minus x square plus 6. So my answer, f of g of x, is minus x square plus 6. Now, let's do the second one. In this case, it is g of f of x. So I have my function g of x, but what's going in the input? Not just x, it's the function f of x. So it's slightly different this time. So I'm going to write g of x first, which is 4 minus x square. Now, wherever there is x, I need to put in the function definition of f of x. So what is f of x? F of x is x plus 2, right? We know that f of x is given to us as x plus 2. So wherever there is x, I am putting x plus 2. Everything else holds. It's a x squared. The term should be raised to the exponent. Nothing changes there, okay? It is literally you're replacing x with f of x, okay? And in the previous case, we replaced x with g of x. And so you're going to do the same. X squared plus 4x plus 4. And this is 4 minus x squared minus 4x minus 4, which eventually gives me minus x squared minus 4x. Now, sometimes we make a check. Is f of g of x equal to g of f of x? In this case, it's not, because what was f of g of x? We got minus x squared plus 6, which is definitely not equal to minus x squared minus 4x, right? So this is just a check. Sometimes you'll be asked to check. And here the two are not equal. So this is as far as composition of functions. It's pretty straightforward. The important things to remember about it is, so what are the important things to remember, right? Important things to remember. Important things to remember. 1, order matters, right? Order matters. Your input is a function and not a variable. And you go inside out. So you start with g of x and then you go outward to f of x. And domain matters. So you have to consider the domain of f of x and g of x, and if there's any constraints, you have to take it into account while doing this. So let us do an example, one more example. So let's do this. F of x is equal to x squared minus 9 and g of x is equal to root of 9 minus x squared. And you have to find the composition. Find the composition f of g of x. So first step, write the definition. It's very easy to get confused which goes on the outside, which goes on the inside. So write the definition. You know that f of g of x is, you start from the outer, right? F, and the input is the inner one, okay? G of x. Okay, that's important to remember. And so what is our f of x? X squared minus 9. So replace x in f of x with the function g of x. So it's going to become root of 9 minus x squared. But remember, you're only replacing the x, so the exponent, everything else stays, right? Now the radical and the power are going to cancel with each other, and you're just going to be left with this. And finally the answer is this. So in this case, f of g of x is equal to negative x square. And that is how you do composition of functions. I will send you some exercises and you can work on those. All right.